Unlocking healthcare insights, data analysis with the HL7 FHIR API. Healthcare data analysis is rapidly changing. The HL7 FHIR API is a key driver of this change. FHIR stands for Fast Healthcare Interoperability Resources. It provides a new way to access and share health information. This standard makes it easier to work with clinical data. Laboratories, hospitals, and clinics can all use FHIR. This helps them exchange patient information securely and efficiently. Data analysis benefits greatly from this improved interoperability. Researchers and analysts can gather data from diverse systems more easily. This leads to better insights and improved patient care. The FHIR API acts as a modern gateway to valuable clinical resources. It uses web technologies that are common today. This makes it accessible to many developers and data scientists. The API allows applications to request specific pieces of health information. This is much better than older methods. Older methods often involved complex custom integrations. FHIR offers a standardized approach. This reduces the effort needed to connect different healthcare IT systems. Analyzing data becomes more straightforward when it is consistently structured and easily accessible through a well-defined API. FHIR's design heavily relies on HTTP interfaces. HTTP is the foundation of the World Wide Web. Using HTTP makes FHIR interactions familiar to web developers. Each piece of health information, like a patient record or a lab result, is a resource. These resources have unique web addresses, much like web pages. Applications can perform actions on these resources. They can create, read, update, or delete information. This is done using standard HTTP methods like get, post, put, and delete. This approach simplifies how systems talk to each other. Clinical resources available through FHIR are extensive. They cover many aspects of healthcare. You can find resources for patient demographics. There are resources for observations like blood pressure readings. Conditions, medications, allergies, and immunizations also have their own resources. Each resource has a defined structure. This structure ensures data consistency across different systems. For data analysis, this means less time spent on cleaning and transforming data. Analysts can focus more on extracting meaningful insights. This helps improve healthcare outcomes and operational efficiency. The blueprint of FHIR API structure and vital security measures. The HL7 FHIR API is built on RESTful principles. REST stands for Representational State Transfer. This is an architectural style for designing networked applications. It uses standard HTTP methods as mentioned before. This makes the FHIR API simple, scalable, and easy to use. Each FHIR resource has a unique Uniform Resource Identifier, URI. Applications interact with these resources directly. The API responses are typically in JSON or XML format. These formats are widely supported and human-readable. This structure is a big step forward for healthcare data exchange. FHIR's architecture is resource-based. This means that health information is broken down into smaller, manageable units called resources. Examples include, and. Each resource type has a specific definition and a set of elements. These elements describe the data contained within the resource. For instance, a resource will have elements for name, birth date, and gender. This granular approach allows applications to request only the information they need. It makes data access more efficient and targeted. This is crucial for effective data analysis. Security is absolutely critical when dealing with patient data. Patient health information is highly sensitive and private. Protecting this data is a top priority in FHIR. The FHIR standard itself does not dictate specific security mechanisms. However, it strongly recommends robust security practices. Implementers must ensure that all data transmissions are encrypted. They must also control who can access the data. Unauthorized access or data breaches can have severe consequences. These include legal penalties and loss of patient trust. Therefore, security must be a core component of any FHIR implementation. Common security mechanisms are often used with FHIR APIs. OAuth 2.0 is a widely adopted authorization framework. It allows applications to access resources on behalf of a user. This is done without exposing the user's credentials. Smart on FHIR is a profile that uses OAuth 2.0. It provides a standardized way to integrate applications with EHR systems. Other security measures include Transport Layer Security, TLS, for encrypting data in transit. Audit logging is also essential. It tracks who accessed what data and when. These measures help ensure patient data remains confidential, integral, and available only to authorized users. Navigating vast data sees pagination in FHIR API queries. Healthcare systems often manage enormous volumes of patient data. Retrieving all this data in a single API request can be problematic. It can overwhelm the server. It can also lead to slow response times for the requesting application. This is where pagination becomes very important. Pagination is a technique used to divide large sets of results into smaller, more manageable chunks. The FHIR API supports pagination to handle these large datasets effectively. This ensures that data retrieval is efficient and reliable. It prevents system overloads. Pagination in FHIR works by returning a limited number of resources per request. When a client application queries a FHIR server for data, the server might have thousands or even millions of matching records. Instead of sending all records at once, the server sends a page of results. This page is a subset of the total results. The client application can then request subsequent pages as needed. This process continues until all the desired data has been retrieved. This makes the interaction much smoother. It also improves the user experience for applications that display this data. To control pagination, FHIR uses specific parameters in API calls. The parameter is commonly used. It tells the server the maximum number of resources to return in a single page. For example, would request up to 50 resources. When the server returns a page of results if there is more data available, it includes links for navigation. These links are typically provided in the resource that wraps the results. There will be a link to get the next page of results, sometimes, and links are also provided. The benefits of pagination are significant for both servers and client applications. It improves server performance by reducing the load of each request. This helps maintain server stability and availability. For client applications, pagination allows for faster initial display of data. Users can start seeing and interacting with the first page of results while subsequent pages are being fetched in the background. It also reduces the memory footprint for the client, as it doesn't have to handle the entire dataset at once. This makes applications more responsive and robust when dealing with the vast amounts of data common in healthcare. Streamlined access patient summaries and targeted field retrieval. Efficient data retrieval is crucial for building responsive healthcare applications. It is also essential for timely data analysis. Requesting entire patient records when only a few pieces of information are needed can be wasteful. This consumes unnecessary bandwidth. It also increases processing time on both the server and client sides. FHIR provides mechanisms to retrieve only the necessary data. This helps in optimizing performance and reducing the data load. Two key features for this are patient resource summaries and the ability to query for specific fields. These make data access much more efficient. The parameter in FHIR allows clients to request a summary view of a resource. Instead of getting the full resource with all its elements, a condensed version is returned. FHIR defines a few standard summary types. For example, returns the resource's narrative and a few key elements, excludes the narrative but includes other essential data elements, just returns the total number of matching resources without any actual resource data. This is useful for quickly understanding the size of a dataset. Using summaries significantly reduces the amount of data transferred. For even more granular control, FHIR offers the parameter. This parameter allows a client to specify exactly which data elements from a resource it wants to retrieve. The client provides a comma-separated list of the desired element names. For example, if analyzing patient demographics, one might request only the patient's name, birth date, and gender. The server will then return a partial resource containing only these specified elements. This is incredibly powerful for optimizing data retrieval. It ensures that only the relevant data points are transmitted and processed, using and leads to substantial improvements in data retrieval efficiency. Bandwidth usage is minimized because smaller payloads are sent over the network. Servers can process these requests faster, as they don't need to assemble complete resources. Client applications also benefit. They receive data more quickly and require less memory and processing power to handle the responses. For large-scale data analysis, these efficiencies add up. They make it feasible to work with extensive data sets and extract insights in a more timely manner. This focused approach to data retrieval is a hallmark of FHIR's practical design. Section 5, Precision in Practice, Mastering FHIR Search Parameters. FHIR provides a rich set of search parameters. These parameters allow applications to filter and find specific resources. This capability is fundamental for any data analysis task. Without precise search, analysts would be overwhelmed by irrelevant data. FHIR search parameters are appended to the resource URL in a query. For example, to find a patient by name, one might use a query like. The server then processes this query. It returns only the resources that match the specified criteria. This makes data retrieval highly targeted. There are many common search parameters defined by FHIR. Some are applicable to all resources, like to search by resource ID, or to find resources updated within a certain time frame. Other parameters are specific to particular resource types. For a resource, parameters like and are available. For a resource, parameters like for the type of observation and for numeric results are common. Understanding these parameters is key to effective data querying. The data type of a search parameter influences how the search is performed. FHIR defines several search parameter data types. These include for coded values and for links to other resources. For example, a search might allow for partial matches, like John D. A search can look for exact dates or date ranges. A search often involves matching a specific code from a terminology system. Knowing these nuances helps in constructing effective search queries. It ensures that the results are accurate and relevant to the analytical need. Using these search parameters effectively allows analysts to retrieve very specific sets of patient information. For instance, one could search for all diabetic patients using a condition code. Then, one could filter them further based on their last HbA1c lab result. This precision is vital for many healthcare use cases. These include population health management, clinical research, and quality reporting. By combining various search parameters, complex criteria can be expressed. This empowers users to isolate the exact data cohorts needed for their analysis. This way, meaningful insights can be derived from the vast healthcare data landscape. Section 6. Advanced Data Journeys, Chaining and Reverse Chaining in FHIR. Sometimes, simple search parameters are not enough. Data analysis often requires looking at relationships between different resources. FHIR supports advanced search techniques like chaining and reverse chaining. These techniques allow for more complex queries that span across multiple linked resources. Chaining allows you to specify search criteria on a resource that is referenced by the primary resource you are searching for. This is a powerful way to follow connections in the data. It helps in building a more complete picture of a patient's health journey. Chaining is done by using a dot in the search parameter. For example, imagine you want to find all observation resources for patients named John Doe. You could search the observation resource. You would chain through its subject element, which references a patient resource. The query might look like, here subject is a search parameter on observation that refers to a patient. The part then applies the name search parameter to that referenced patient resource. This allows for filtering observations based on properties of the associated patient. Reverse chaining is another powerful technique. It allows you to find resources based on criteria of other resources that refer to them. This is done using the search parameter. For example, you might want to find all patient resources who have had an observation for a specific low-INC code. For example, for blood glucose, recorded in the last year. The query could be, here indicates that we are looking for patients who are referenced by an observation that meets the specified code and date criteria. These advanced search techniques, chaining and reverse chaining, greatly enhance the capabilities for patient data analysis. They allow for the construction of sophisticated queries. These queries can uncover complex relationships and patterns within the data. For instance, analysts can identify patients with a specific condition who are also on a particular medication, or they can find patients who have had certain procedures performed by a specific practitioner. This ability to traverse resource relationships directly within a query is invaluable. It simplifies data retrieval for complex analytical scenarios. It helps researchers and clinicians ask more nuanced questions of the data. Section 7. Cloud-powered analysis, helper functions, and Spark caching strategies. Modern healthcare data analysis often involves large datasets. These datasets are frequently stored in cloud environments. Cloud storage offers scalability and flexibility. To work with this data effectively, specialized tools and techniques are needed. Setting up cloud object helper functions is a common first step. These functions provide an easy way to read data from and write data to cloud storage services. Examples include Amazon S3, Google Cloud Storage, or Azure Blob Storage. These helpers abstract the complexities of interacting with cloud storage APIs. When processing large amounts of FHIR data, especially in distributed computing frameworks like Apache Spark, helper functions are very useful. Spark is often used for large-scale data transformation and analysis. The helper functions can be used within Spark jobs to load FHIR data, perhaps stored as JSON or Parquet files, from cloud storage into Spark data frames. This allows analysts to leverage Spark's powerful processing capabilities. For example, a helper function might handle authentication with the cloud provider. It might also manage efficient data streaming. This makes the overall data pipeline more robust and easier to manage. Caching data in Spark is a crucial optimization technique. When you read a large data set from cloud storage, the process can be time-consuming. If you need to access the same data multiple times in your Spark application, for example, for iterative machine learning algorithms or multiple queries, rereading it each time is inefficient. Spark allows you to cache a data frame in memory or on disk, or a combination of both. Once cached, subsequent operations on that data frame will be much faster. This is because Spark can access the data from the cache instead of going back to the original source. Caching significantly speeds up analytical workflows. Understanding the structure of FHIR resources is essential for analysis. FHIR resources often have nested structures. For example, a patient resource can have multiple name entries, each with given and family parts. It can also have multiple address entries, each with line, city, state, etc. When this data is loaded into a Spark data frame, these nested structures are preserved. The method in Spark is very useful here. It displays the schema of the data frame, including all nested fields and their data types. This helps analysts understand how to access specific data elements within the complex FHIR JSON structure. It is a fundamental tool for data exploration and preparation. Section 8. Building the full picture, large datasets and longitudinal patient records. Analyzing large datasets is fundamental to unlocking deep insights in healthcare. The sheer volume of data generated by healthcare systems presents both a challenge and an opportunity. FHIR, by standardizing data representation and access, makes it more feasible to aggregate and analyze these large datasets. This data can come from various sources. These include electronic health records, medical imaging systems, wearable devices, and genomic sequencers. Harnessing this data effectively can lead to breakthroughs in understanding diseases. It can also help in developing new treatments and improving patient care delivery. A key goal in healthcare data analysis is the creation of longitudinal patient records. A longitudinal record provides a comprehensive view of a patient's health journey over time. It consolidates information from various encounters, providers, and care settings. This includes diagnoses, medications, procedures, lab results, and lifestyle data. Building such a record requires careful integration and chronological ordering of data points. FHIR resources, with their clear temporal elements like dates and periods, facilitate the construction of these time-based views. A complete longitudinal record is invaluable for truly understanding patient health trajectories. Constructing longitudinal patient records from disparate FHIR data sources involves several steps. First, patient matching is crucial. This ensures that records belonging to the same individual are correctly linked, even if they come from different systems with different identifiers. FHIR's patient resource and identifier systems help with this. Next, relevant clinical data like observations, conditions, medications, etc., needs to be gathered for each patient. This data then needs to be ordered chronologically. Finally, it needs to be structured in a way that supports analysis over time. This might involve creating timelines of events or summarizing health status at different points. The analytical power derived from longitudinal patient records is immense. Researchers can study disease progression and treatment effectiveness over extended periods. Clinicians can gain a deeper understanding of their patients' histories. This helps in making more informed clinical decisions. Population health analysts can identify trends and risk factors within specific patient cohorts over time. For example, they can track the impact of public health interventions. Ultimately, the ability to create and analyze comprehensive longitudinal views of patient data is transformative. It moves healthcare towards a more proactive, personalized, and evidence-based approach to care. Section 9, The Future of Health AI, FHIR, Data Accessibility and Predictive Power. The journey through mastering HL7 FHIR for data analysis culminates in its application to advanced fields like artificial intelligence. FHIR's role in standardizing data exchange is a cornerstone for making healthcare data more accessible. Accessibility is a critical prerequisite for any successful AI or machine learning initiative. Without well-structured, easily obtainable data, building robust and reliable AI models is nearly impossible. FHIR helps break down data silos. It provides a common language for health information. This significantly lowers the barrier to entry for developing innovative AI solutions in healthcare. Well-prepared data is the fuel for machine learning algorithms. FHIR not only makes data accessible but also provides a consistent structure. This structure simplifies the data preparation phase, which often consumes a significant portion of an ML project's timeline. When data is in FHIR format, less effort is needed for transformation and cleaning. Data scientists can more quickly move to feature engineering and model training. The standardized resource definitions mean that data elements have consistent meanings across different sources. This improves the quality and reliability of the data used for training ML models, leading to more accurate and generalizable results. The potential of predictive modeling using FHIR data is vast. Machine learning models can be trained on large FHIR-formatted datasets to predict various health outcomes. For example, models can predict the likelihood of a patient developing a specific disease. They can identify patients at high risk of hospital readmission. They can also forecast adverse drug events. These predictions enable proactive interventions. Clinicians can take preventive measures for at-risk patients. Healthcare systems can optimize resource allocation. This leads to improved patient outcomes and reduced healthcare costs. FHIR provides the data infrastructure to support these advanced analytical applications. In conclusion, HL7 FHIR is more than just an interoperability standard. It is a catalyst for transformation in healthcare analytics and AI. By enabling seamless data access and promoting consistent data structures, FHIR empowers researchers, clinicians, and data scientists. They can unlock new insights from complex health data. The ability to efficiently query, retrieve, and prepare data using FHIR APIs, including advanced search and handling of large datasets, is paramount. As FHIR adoption continues to grow, its impact on fostering data-driven healthcare and enabling sophisticated machine learning applications will only become more profound. The future of medicine will be significantly shaped by this enhanced data liquidity.